So we attempt to derive that curve or radiation spectrum from classical statistical mechanics. Okay. So how do we do this? First, I'm going to state without proof that you can show that the spectrum of a black body when heated up. So, when you heat up a black body, what happens is that that chamber that we saw, it fills out with radiation. It fills up with radiation, right? Because all the atoms which make up the wall of that black body, they start oscillating and they emit radiation. And, this whole object kind of, fills up with electromagnetic radiation. But, some of this radiation then leaks out, right? And what we do is that we do a spectral analysis of the radiation that is leaking out. And that is basically what we call the black body radiation, the spectrum. Okay, so so the spectrum of the black body when heated up is independent of the shape and the dimensions of the cavity, as long as the cavity is large enough. Okay. So this is a result from classical statistical mechanics that we can adopt. And what it means is that we can then just do, for the convenience of our calculation, we can just take our cavity to be a cube whose sides are of length L. Okay. So when we heat up the black body, what we can assume is that the atoms and the molecules and the walls, they will vibrate and they will create electromagnetic radiation. But this electromagnetic radiation, they will, at a steady state, these electromagnetic radiations will form standing waves. Okay. And it's by considering these standing waves, each standing wave as a mode, as a degree of freedom, that we can calculate the energy that is contained in this electromagnetic field. Okay. So what we do is that we take the propagation vector k, and k has 3 components, x, y, x, kx, ky, kz, and k is related to the wavelength by 2 pi by lambda. And because we are considering standing waves, it must be that kxl must be 2 pi n of x, where n of x is an integer. Okay, And similarly, K of Y of L must be 2 pi ny. K of Z of L must be 2 pi nz. So what are we saying? We are saying that, okay, we have a cavity like this, and we are filling it up with, wavelengths. And these wavelengths, because they're standing waves, the number of wavelengths that they can accommodate has to be an integer number of wavelengths. Okay? If not, they will not form a standing wave. Okay? You might say, why not half integer, half a wavelength? If it's a half wavelength, then they will reflect and they will interfere with itself, and it'll give you a 0. It will not give you a standing wave. And that's why we need full wavelength. Okay? So here, nx and ny and nz, these are integers. Okay? So we can think of each standing wave as a degree of freedom. Okay, and if you do that, we can now apply the principles of statistical mechanics to find out how much energy we can associate to each degree of freedom. Now, this is given by the equipartition theorem.